All right. Hello, everyone. My name is Bernd, and today is day 6 of Advent of Code. And today's puzzle was about boat races. So our input is a bit simpler this time, and we just got a few races. And for each of those races, we're given the time the race lasts for in milliseconds and the best distance someone has achieved. So the record distance that has been achieved in the past. And the race works the following way. So if we have, for example, 7 milliseconds, we're allowed to spend some amount of those milliseconds charging, and the rest of the race will be moving, and the speed is corresponding to the time we spend charging. For example, if we have the first race that lasts for 7 milliseconds, we can spend the first 3 milliseconds charging the boat, and then for the last 4 milliseconds, it will move, and the speed will be 3 millimeters per millisecond. So the total distance would be 3 times 4 equals 12. So that's larger than the current record. So in this case, we would beat the record if we charge a boat for 3 milliseconds. For the puzzle itself, we are interested in how many options we have of charging the boat in such a way that it does beat the previous record. And then we evaluate this for every single race. And in order to get the solution, we just multiply those values together. Okay, so how can we do that in Python? Of course, we need to read the file and split it into lines. And then we can parse those lines. So this time I used regular expression. So we can look for that symbol. D means digit, so from 0 to 9. And then plus means multiple of them in a row. So in order to find in this race time string to find all the integers without a sign this time, we can apply this function, and then this will give us all the strings which just consist of purely of digits, and then we can convert that into a number in order to get all the integers in the line. So that way we can parse the first line in order to get all the race times, and parse the second line in order to get all the race records. Can do a quick check for the line for the parsing, and that looks good. So it does give us those times and those distances. Okay, then with this we can try to solve the problem. So of course we pass the line into the race times and race records, and then we go for each single race, and this will have then a race time and the race record for this particular race. And then we get the number of possibilities that we can choose our charging time in order to get the record and get a new record. And then the solution would be all the product of all of those. So we multiply the current solution with this value. In order to get the number of possibilities given with the formula for a given race, so the numbers for the first part are fairly small, so we can just iterate through all of them. So we just go for the charging time in the range from 1, and the last is race time minus 1, for example. And then we can just calculate. The moving time will be the race time minus the time we spent charging at the beginning. The distance will then be the product of those two values. And then we check if the distance is larger than the race record. We have a new record, so we have the number of possibilities will increase by 1. Okay, we can run that on the test input, and that looks good. So we can also run it on the real input, and it also gives us the right solution. For part 2, it turns out for part 1 we read the input the wrong way. So we thought it was 3 different races, but in reality we're supposed to ignore all the white spaces and just read it as one single number. So what the input actually means is there's one single race with this time that will last for this many milliseconds, and the record distance so far is given by the second line. Okay, so how can we figure out this time? So since the numbers is larger, it would take much longer to iterate through every single number and check. So what we can do is, so in order to do it a bit smarter, we can do something else. So first we will define this function whether a particular charging time beats the record. How can we, that's similar to what we used in part 1. So again, we have the moving time will be given as the race time minus the charging time, and then the speed will be equal to the charging time. So the distance we will travel or move is equal to the product. And then what we want to know is that whether the distance is larger than the previous race record. And then we can see that the distance is a quadratic function of the charging time. So we could just solve the quadratic equation. I wasn't particularly excited to do that, so I did a slightly similar, I did a different approach. by just doing some kind of binary search. So how did I do that? So we've used the same function as part 1 to parse the lines, but then this time we have one single racing time, which is made up of all the racing times we had for part 1. So how do we combine them into a string? We just take each number, convert it into a string, join them all together into one large string, and convert that into an integer. And similar for the race record. So this will give us one race time and one race record for the single race we're considering in this part. And then because this is a quadratic equation of this form, of like race time minus charging time times charging time, turns out that the best charging time will be the race time divided by 2. And then at first check, we can check whether this best charging time actually beats the record. If it's not the case, then we're never able to beat the record, so we return 0 possibilities. Otherwise, we want to do some binary search to find the lowest charging time that will give us a record. So in particular, we can have this function which takes as an input one value which does not give us a record and one value which does give us a record, and then this function that tells us whether a particular integer t, a particular charging time t, actually beats the record or not. So that would be given by this function which just takes one integer t and calculates whether t beats the record based on race time and race record. Okay, let's look at the implementation of this find lowest above. So again, we have the lower, which is definitely below, which is the upper, which is above. And then we have this is above function, which tells us whether a new value is below or above. First, we can check if the upper is just one larger than the lower, this number that is below. If this is the case, then we know the first one above is definitely the upper because lower is below and upper is above, and there is no number in between. Otherwise, we will consider a new number which lies in the middle of the upper and the lower number, and then we check whether this middle number is above or below. If the middle is above, then we also know that everything between middle and upper is above as well. So in order to find the lowest above, we only need to consider the interval from lower to middle. Similar, if middle is below, we know that everything from lower to middle is below as well, so we don't need to consider this interval, and we only need to consider the interval from middle to upper in order to continue our search. And then this will recursively call the function itself and eventually return the lowest charging time, which still beats the record. And then because of the symmetry in here, so if we replace charging time with race time minus charging time, this will be the same distance. Because of this symmetry, we can also immediately calculate the highest charging time with a record, which will be the total race time minus the lowest charging time with a record. Knowing this, we can figure out the amounts of possibilities for choosing a charging time. So we know that first we consider all the values from 1 up to the highest charging time with the record, but then we need to subtract all the values which are below, and this amount will be lowest charging time minus 1. So this term will give us the number of possible ways of charging in order to beat the record. And we should run a little test to check whether that actually worked out. So it looks good. So our program works on the test input, so we can also run it on the real input. And it also turns out it gives us the right solution. Okay, that's it for day 6. I hope you enjoyed today's puzzles. Best of luck in the future and see you around.